Okay, hello everyone. My name is Yaoshu Wang, and I'm a researcher in Shenzhen Institute of Computing Science. Today, I represent a paper whose title is Learning and Deducing Temporal Orders. First, I will introduce the background of our project. Currently, the need for determining the currency of data is important. There are many applications that need the latest data. For example, in healthcare domain, doctors always need the latest information of patients for their accurate diagnosis. The second is the search engine, such as the Google. They always need to collect the latest information, and the users always expect to search the latest news and for their need. The final error is the final domain is some error of the decision making, relativist decision making, and experts always need to collect some up-to-date information to make their judgments and the final decisions. So bank is one real-life applications. So when processing the business laws, banks always need to inspect the latest information of their customers. After that, they could make their final decisions. However, there are mainly three issues to determine the up-to-date information. So we can see the right table. There are 6 tuples that belong to the same person, Mary Goldsmith. We can see that as time goes, there are some attributes such as address, status, job, keys, and SA, which means the shoe size. This attribute, the value of this attribute changes. So the yellow region records the timestamp. The first issue is that there are some cells whose timestamps may not be recorded, which we call the missing timestamps. There are also some timestamps. We can see this year region. So this timestamp only records the years, but their months and days are missing. So we call this the imprecise timestamps. The final issue is incorrect timestamp. You can see that in this cells, the year is the 2000, which is inconsistent with the timestamps of other values in the same attributes. So we can deduce that this timestamp is inaccurate. So to address this problem, we need to deduce or find the latest informations, the latest values of each attribute. So in this paper, we mainly have 4 conclusions. The first one is that we define the notion of temporal orders on attributes, and the formula formulates the problem for determining temporal orders. Secondly, we propose a creative framework called GATE to determine temporal orders by combining deep learning and logic deduction. The third conclusion is that we propose a deep learning model to learn temporal orders on attribute values. Finally, we design a creative path in GATE, which could discover rules and deduce more temporal rules with the trace mechanism. Okay, now I will introduce the notion of temporal orders. A temporal order on attribute A of a relational table D is a partial order such as for all tuple T1 and T2 that belong to D, and we use this expression to donate the temporal orders. So if the value in the attribute A of T1 is at least as current as attribute A of T2. So we can see there are 2 examples. So we use temporal order to determine the status of the timeless of status, single and married, or some different values of addresses, such as the 7th Avenue or the 6th Constant Avenue. Okay, now I will introduce the predicates. Predicates, we donate P. We use P to donate the predicates, and it consists of 3 parts. The first is the constant predicates, where C is constant in the attribute A, and the second part is a non-constant predicates. So we use a comparison operator to connect or compare 2 values, the value of attribute A between 2 attributes T1 and T2. So the final part is a temporal order, which is also a timeless predicate, such that it compares the timeless of attribute A of T1 and T2. So after the definition of predicates, so we can now define our timeless rules. We call it the currency constraint, which is CC for short. CC is the first order logical rule defined as X deduced P0. Here, X is a precondition, which is also a conjunction of the predefined predicates. And P0 is a consequence, also a single predicate over the database schema R. In particular, we have M tuple variables. So firstly, these M tuple variables should belong to the same attributes, so their EID are the same. And secondly, all of them should satisfy the precondition. Then all these 2 conditions are satisfied. We can deduce the TU is earlier than TV in attribute A. So which is the P0 is the temporal order or the timeless predicate. Okay, now I will give some examples of currency constraints. So the first currency constraint is related with monoptonicity, such as if some numerical values have some orders, we can deduce that this order, the numerical orders, it had the same correlation with the timeliness, such as the 6 is smaller than 7. So that means the timeliness of, as I say, timeliness of T2 is earlier than timeliness of T4 in the attribute S3. The second example is about the same correlation of attributes. So if the T1, T2, such as in this example, T1, T3 has the same time order, such as single is earlier than its const. So this the time orders also hold in the attribute address. We call these rules as the comonotonicity. The third example is about the transitivity, such as if the timeliness of T1 is earlier than that of T3, and also T3 is earlier than the T5. So we can, according to the transitivity, we have T1 is earlier than T5. So, and we use these rules to represent the transitivity relations. Finally, we can use the constraint to correlate different attributes, such as given two attributes T1, T2, and if one attribute is married and the other attribute value is divorced. Also, we can find that the case such as 1 is smaller than 2, so we can deduce that the married is earlier than divorced. So this is a global time order. Okay, now I will define our problem, such as given a temporal instant D, which is also original table, and we also define some attributes that should have timeliness, such as the last name, address, status job, and the shoe size. And we also have some timestamps, such as the yellow one is the existing it's a set of existing timestamps. The output that we want to find the orders of each attribute, such as in address. So we can find that this the last attribute. So the attribute, the value of T6 is the latest one, and which is the later than T5, T4, and T1. So so the output is to find the time orders of all attributes, all tuples. So the main idea in our paper, the main idea is that deep learning could find time orders, but predictions are not always reliable. So especially in the low resource setting, which means that there are not many existing timestamps. So the CC rules could deduce more time orders, but the CCs largely depend on existing ones. How to combine them and make use of the advantages is the main aspect of this paper. Okay, so now I introduce our framework, which is the creator and critic framework, which is called GATE. So in this picture is architecture of the GATE. So we have the GATE mainly consists of a creator and critic. So in the creator mainly train a ranking model to predict the time orders. So its input is the time instance and all existing time orders. The second input is the augmented training data, DAUG. So the output is the prediction orders of the remaining time orders. So the critic part, the critic deduces more time orders by applying CCs via the chase mechanism. So the input is also the time orders and the existing, is also the original table and the existing time orders and T. And we also fit some CC rules into critic. The output is the new time orders, also called augmented data, DAUG, which is the set of more time orders deduced by CCs and the existing ones. So here, this is an example. So firstly, the critic used we can see that this table is the temporal instance, and firstly, critic used the time orders and the existing timestamp to collect training data and deduce more time orders with CCs. So here CCs are the given, so which can be discovered by some discovery mechanism. The secondly is that the critic extend the existing timestamp with timestamps with the set of deduced time orders, the DAUG. So we merge them and into the DT, and we pass the DT to the creator. So the creator sends the augmented training data to the creator. So now after the creator received the training data, which is also a set of time orders. So the creator train is the model, which is a ranking model incrementally based on the DT, the training data. Then after training, the creator predict more time orders with the remaining of all the remaining data, and send the predicted time orders to the critic. After the critic receives some predicted time orders from the creator, the critics deduce more time orders will chase using the CC rules, and then the critic after chasing, the critic will construct the augmented training data and also pass them to the creator. So we can see that from line 2 to line 11, we can process iterative until the critic cannot construct more augmented data, and then the iteration terminates. So the termination condition, the condition of termination is that there is no new augmented data. Okay, so now after that, we introduce the two parts, the creator and critic. So the critic is a machine learning model, which is a deep learning model. And firstly, with the table as input, firstly we serialize it to a sequence with this formula, and then we pass the serialized sequence and to a pre-trained language model such as BERT, and then we get some embeddings, and then we use the embeddings to make some average or some other operations, and to generate the embeddings of. So you can see that we can the target vector is the schema. So the merit, you can see the merit is the one is embedding. So this embedding is the vector of value merit, and we can see that this vector is the embedding of the birth. And we use this loss function to determine their orders, which we call attribute-centric adapted pairwise ranking. And we use this ranking loss, the pairwise ranking function to train the model, such that the creator could predict the order of two attributes in the same two value in the same attribute. And after that, given a tuple pair T1, T2, and the closed function, the creator could adopt the confidence to measure the confidences of the time order of T1, T2. And we use this expression as the closeness function. And if if the confidence is larger and not smaller than a predefined value, and we see this is true, and pass them to the critic. Okay, now in the critic part, the input is a timer instance dt, and the set of prediscovered CC rules, and the predict time orders by the creator, and the output is the more time orders find deduced by the critic part. We'll have an example. There are two rules. There are two CC rules, and we have the yellow region are timestamps, the existing timestamps. You can see that we have 3 time orders, and we use this phi1, the CC. The pi1 as the first rule, and we can deduce the more time orders. The Mary is earlier than divorced, and then we use the pi2 as the second rule, and to deduce the more time orders via trace, and then we use these time orders to these time orders to deduce more time rules. So the time orders in blues are the new time orders the critic deduced. Okay, so in experiments, we mainly use the full data size, and we compare with some variance of gates, and also some ranking models and rule-based methods. So firstly, we find that the F measure of gates increases with more rounds in most cases. Secondly, the gate outputs creator and critic by 7.8% and 34.4% in F measure on average. Finally, gate is better than certain rule in ProSense, which are rule-based methods, and RankBERT and DitoRank, which are deep learning methods. We also make experiments by varying k and varying the size of schema, which is a set of rules. So we find that gate consistently achieves the highest MAP at k, which is a ranking criteria. Secondly, F measure of gate increases with more CCs because gate needs CC to generate more augmented training data. Finally, we also compare the efficiency of gates. So gate beats the gate NC, which is a baseline, also a variance of gates. Gate beats gate NC in efficiency by 8.5 times on average. Secondly, gate has competitive over time against some baselines. So in conclusions, we have studied how to determine time orders. So our noting consists of, firstly, the definition of time orders and the formulation of the problem for determining time orders. Secondly, we propose a critic framework that effectively and efficiently combine deep learning and the logic deduction. Thirdly, we propose a novel deep learning model to learn time orders. Finally, we designed a rule deduction algorithm that deduces time orders with trace mechanism by using CCs. And also, our experimental study have shown that the methods are promising. Thank you everyone.